Welcome to Networks Professionals.
Welcome to this explainer. When we talk about AI today, it's so incredibly easy to just picture it as lines of code floating around somewhere up in the cloud. Software algorithms, digital brains. It almost feels like magic, right? But the truth? The truth is actually grounded right here in the physical world, in these massive, power-hungry data centers generating an immense amount of heat. The artificial intelligence revolution isn't just a software revolution. It is fundamentally driven by incredible, highly specialized physical hardware. So today, we're going to be unpacking the physical engine of AI, taking a close look at the actual silicon that makes all of this possible. Okay, let's dive into this and decode the hardware ecosystem. Here's our roadmap. We're going to start with the deep learning bottleneck, look at GPUs for parallel power, explore Google's custom TPUs, check out everyday NPUs and edge AI, and then finish up with exactly why all this specialized hardware matters so much. Section 1. The deep learning bottlenecks. To really grasp why specialized hardware even had to be invented in the first place, we first have to understand the massive conflict sitting right at the heart of modern computing. Deep learning models require calculating billions and sometimes literally trillions of parameters just to produce a single output. Traditional CPUs, well, they process tasks sequentially. They handle instructions one by one. And this brilliantly illustrates the problem because it hits a massive bottleneck. It's kind of like forcing a massive multi-lane highway through a single toll booth. Specialized AI hardware fixes this entirely through parallel processing. Instead of one by one, these chips perform thousands of calculations simultaneously at unprecedented speeds. It's essentially like opening 10,000 toll booths all at the exact same time. The results of changing this physical math are absolutely staggering. A massive deep learning model that used to take months to train on sequential hardware now takes mere hours with parallel processing. Just think about that for a second. What used to be a quarter of a year's worth of iteration can now be finished before a team even logs off for the weekend. That completely, fundamentally changes the pace of global innovation. Section 2, GPUs, the parallel powerhouses. Now, what's really interesting about this slide is how the market shapes up. While GPUs were originally designed for rendering millions of pixels in video games, that exact parallel architecture made them absolutely perfect for deep learning. Today, NVIDIA is the dominant force here. Their data center chips, specifically the Hopper H100 and the newer Blackwell B200 architectures, are pretty much the industry standard for training the massive large language models that we interact with every day. But the competition is definitely fierce. Heavyweights like AMD with their Instinct MI300 series and Intel pushing hard with their Gaudi accelerators are fighting tooth and nail for data center dominance. You can think of GPUs as your general-purpose heavy lifters. Because of their highly parallel architecture, they are just best utilized for general-purpose AI training, large-scale model development, and high-performance computing. Basically, if you're a developer building a foundational AI model from scratch and you need a raw, versatile, parallel power, GPUs are your absolute go-to hardware. Section 3. TPUs, Custom AI Silicon. While GPUs are those versatile powerhouses we just talked about, the industry is also pushing heavily into hyper-specialization. Enter the ASIC, an application-specific integrated circuit. Now, unlike a general processor, an ASIC is hardwired for one single job. Google built their Tensor Processing Units, or TPUs, by stripping away all those general capabilities just to do one thing perfectly: matrix operations, or tensors. By hardwiring the silicon exclusively for the specific math used constantly in neural networks, they maximize both speed and energy efficiency for deep learning tasks. It's a highly targeted tool for a highly specific job. Now, because they are Google's proprietary tech, you access these via the cloud. You aren't exactly dropping one of these into your desktop PC at home. But they are absolute monsters for high-volume specific workflows. If you're running TensorFlow, if you're fine-tuning massive models, or doing high-volume inference, where an AI is deployed and answering millions of users simultaneously, TPUs are just brilliant in these exact environments. Section 4. Everyday AI, NPUs, and Edge. So far, we've talked about giant, power-hungry servers sitting in massive data centers. But the hardware revolution is actually happening locally too. On one hand, we have NPUs, neural processing units. These are built directly into consumer CPUs and phones, so your device can handle AI tasks locally without constantly pinging a private server. On the other hand, we have custom edge chips from companies like Halo and Sema.ai. Let's move to and see how this builds across our physical spaces. NPUs are already living right in your laptop and phone processors, inside the Intel Core Ultra, AMD Ryzen AI, or Apple Silicon chips. But step out into the real world, and custom edge chips are running real-time computer vision and smart cameras, they're powering the complex navigation of autonomous factory robots, and they're keeping self-driving vehicles safe on the road. The hardware out there must be compact, entirely local, and incredibly energy efficient. Section 5. Why specialized hardware matters. So the crucial point is this: specialized hardware bypasses traditional computing bottlenecks, allowing AI systems to ingest vast datasets, learn patterns, and make predictions at unprecedented speeds. Every single piece of that mind-bending AI software we rely on, from conversational chatbots to rapid image generators, is entirely bound by the physical limits of the silicon. Without the parallel processing of GPUs, the custom-wired architecture of TPUs, or the local efficiency of NPUs, the software simply hits a wall. Which brings us to a really fascinating frontier. As specialized silicon continues to bypass traditional hardware limits, what new AI breakthroughs will the next generation of chips make possible? I mean, when engineers manage to shrink the hardware even further, drop the power consumption, and stack even more parallel operations into every square millimeter, the software is only going to get more capable. The physical limits of AI are being pushed every single day in these fabrication labs, and it is absolutely thrilling to imagine what they will engineer next. Thanks so much for joining me on this explainer. I hope you found the physical side of AI as fascinating as I do, and I will see you next time.
Thanks for watching.